Come back. So here is an example. Julia enjoys jogging. She has been jogging over a period of several years, during which time her physical condition has remained constantly good. Usually, she jogs 2 miles per day. The standard deviation of her times is sigma equals 1.80 minutes. During the past year, Julia has recorded her times to run 2 miles. She has a random sample of 90 of these times. So she recorded her run, her 2 mile run, 90 times. For these 90 times, the mean was 15.60 minutes. That is the average amount of time it took her to run 2 miles. Average over what? 90 times. Okay? Let mu be the mean jogging time for the entire distribution taken over the entire year. Okay, year has more than 90, right? It has 365 days and so on. Find a 0.95 confidence interval for mu. 0.95 meaning 95% confidence. So the question is basically to estimate her mean over the entire year, not just the mean over 90 times, over the entire year. Well, we may not be able to find precisely, but we may be able to find an interval with 95% confidence that will contain mu. So we have a simple random sample of running times. Sample size n is 90. It is large enough. Okay, so notice we don't know anything about her time, whether it's normal distribution or anything, but our sample size is large enough, so we can say x bar is approximately normal. We also know standard deviation. Okay, so standard deviation is 1.80. Okay, we also know standard deviation. It is appropriate to use normal distribution to now find the confidence interval. All right, so confidence interval of 95%. So for 95% or 0.95, the critical value is 1.96. Okay, so now you are going to use this critical value and you are going to use this n, you are going to use this sigma to find E. Okay, error tolerance. That's your formula. ZC, sigma, and square root n. That gets me approximately 0.37. Given this value, you already knew your sample mean and you have found a tolerance, error tolerance. So you take the mean, sample mean, subtract this, and another number you get is mean, add it. So one is subtract, the other is add. Okay, so this is the mean, this is for the mean. All right, so you took the sample mean, subtract error tolerance, sample mean, add error tolerance. Your mu is written between these two. What is the interpretation? So this is carefully worded, guys. Mind this carefully. We conclude with 95% confidence that the interval from 15.23 minutes to 15.97 minutes is one that contains the population mean mu. So 95% confidence level, we say that this interval is one which contains mu. Okay. All right. How do we come up with sample size for estimating mu? Well, in the design stages of statistical research projects. Okay, it is a good idea to decide in advance on the confidence level you wish to use and to select the maximal margin of error E. So far what we have done is we started with a sample size and proceeded and whatnot, right? But where before you start any study, it's better to know your confidence level and the allowable margin of error. So maximal margin of error. How you choose to make these decisions depends on the requirements of the project and the practical nature of the problem. Okay. Whatever specifications you make, the next step is to determine the sample size. So sample size is something that you make, the decision on the sample size is something you make after you have decided upon margin of error, maximal margin of error, and the confidence level. Okay. Now solving the formula that gives maximal margin of error E enables us to find the minimal sample size. So minimal sample size is square of this fraction. Okay. So I don't need x bar yet, you see, but we are assuming that this distribution of sample means is approximately normal. That's the requirement. So n is ZC sigma over E power 2. So ZC is the critical number, critical value for the given confidence level. Sigma is population standard deviation. E is the specified maximal margin of error. This can sometimes, most of the times, be a decimal. It doesn't have to be a whole number, but you would round it up to the next whole number. This n will be the minimal sample size. All right, let's look at an example. You're conducting a wildlife study designed to find the mean weight of salmon caught by Alaskan fishing company. Preliminary study of random sample of 50 samples showed me S, that is the sample standard deviation, to be 2.15 pounds. How large a sample should be taken to be 99% confident that the sample mean X bar is within 0.2 pound of the true mean. All right. First find the critical value for 99%. Okay. So critical, not that one. Okay. Use the table to find the critical value for 0.99. You will get this. E is given to be 0.2. That's the error that we are allowed, maximum error. Okay. Now, preliminary study of 50 fish is enough to permit a good approximation for sigma. See, we did not know sigma, but we started with 50 salmon and showed that the standard deviation for my sample is 2.15. So I'm taking that as an approximation for the population standard deviation. Okay, now we are going to find n by plugging in these critical value, sigma E square. So the next biggest number, so this is a decimal, you see, you need 770. In determining sample size, any fractional value of n is always rounded to the next higher whole number. So we concluded that a sample size of 770 will be large enough. Okay, so a sample size larger than 770 is also fine. So this is basically the bare minimum you need to get working on your studies. All right. So this completes section 8.1 Let's continue with problems in the next videos. Until then, bye.